So buckling, it happens very often. It's a very common failure mode. In fact, most aircraft structures are designed for buckling, or the percentage of a structure designed by buckling or stability-related requirements is much larger than anything that's failure-related, except potentially for damage tolerance, which is the second most common failure mode that designs structure. And if you are careful about it, you can actually use it to your advantage and save weight when you do post-buckling, and we'll talk about post-buckling in either the next lecture or the lecture after. We will start with a problem that is a rectangular plate, simply supported all around, so the displacement out of plane is 0, under biaxial loading. And this plate has symmetric layup, so the B matrix is 0, and the D16 and D26 are again 0. And we are following basically the approach. It's in the book in detail, but it's mostly taken after the approach by Jim Whitney, who wrote a book on structural analysis of laminated anisotropic plates. Basically, between him and a couple of other guys, everything that people do in composites is a repetition. These guys discovered everything, and we are just rediscovering the wheel in different small variations. We are doing this problem because then if you can solve the biaxial problem, then the uniaxial problem is just a special case of this. And because it has some interesting characteristics. Of course, if my loading is tensile in both directions, at least for a metal, you cannot buckle it. If you apply tension in both directions, then it just extends in both directions. If one of the directions has compression, then you can get it to buckle. Now, in composites, for some layups, you can actually get them to buckle even if you have biaxial tension, but that's quite rare, and it's not done very commonly. Usually, either both of them are compression, or one is tension, the other compression, and that way you can actually get a buckling solution out of it. Now, the governing equation is this one, which is the green equation we saw before. Let me show it again. So if you look at the bottom here, we have exactly the governing equation in which the distributed loads Px, Py, and Pz are 0. Px, Py, and Pz are 0. And for our problem, we do have Nx applied, we do have Ny, but our Nxy is 0. So if I take this equation and remove these terms, I will end up with this governing equation for W. My boundary conditions, remember, now simply supported, and that means my W is 0 all around the edges. But also, in the strict definition of simply supported design, where we allow the edges to rotate freely, there are no bending moments there. So the Mx is also 0 and the My is 0. So, in fact, these are the full set of boundary conditions. And why do I have 4 of them? Because it's a fourth order differential equation. As you might expect, when in doubt, you assume an infinite series with sines and cosines. And because it's a simply supported, if you assume this, then you satisfy all the boundary conditions, both on W and on the moments, because the moments, Mx, My, and so on, are just second derivatives of W, either with respect to X or with respect to Y. So if W is 0 at the edges, the second derivatives will reproduce the sine terms, and therefore they will also be 0 at the edges. So automatically, with this infinite series for W satisfies our boundary conditions. So I substitute this in my governing equation here, and I factor out the sine m pi x and sine n pi y over b. So if I factor that out and I cancel it from both sides, I will get this mess on the left-hand side equal to this mess on the right-hand side. Basically, that involves the AMN on both sides, and that's not very encouraging because AMN would cancel. And it involves the AR, the aspect ratio. A over B is the length along which the load is applied, B is the width, and we call it AR aspect ratio. Now, one solution says AMN equals 0, and that means my W is 0, so I only have in-plane deformation, stretching, and so on. That's fine, but if we're trying to do buckling, that's not the one we want. And the other is AMN is different than 0. So if AMN is different than 0, I have to find a way to satisfy this equation. And before I do that, for convenience, I introduce this notation. NX, if it comes out positive, it means I have tension. Since I want the compressive load to be expressed as a pure number, I call NX minus N0, completely arbitrarily. That means if my answer is in terms of N0, and N0 comes out positive, then I have compression. And I then introduce this NY is minus K N0. Basically, I'm saying that NY is K times NX. So for one value of K, I can find an answer. If I change that value of K, then the answer will change. So if I take this equation here, and there is no sun over there, I can solve for NX, which I can write in terms of N0, and I will find this expression. This expression says my buckling will occur when N0 is equal to this quantity, which is a function of that K. So the amount of NY load obviously affects my buckling load, and the more my NY increases, this K would increase, so the buckling load would go down, for example, for a case of biaxial compression. Notice where the aspect ratio appears in all over the locations, and that's significant because as I change my aspect ratio, we'll change the buckling load. We'll see that in a little bit. And notice the M and N. Now those are important. Let me briefly mention them now, and we'll talk about them some more later on also. This is my M and this is my N. Sine M pi x over A basically means a function that between 0 and A just simply does one half wave. So if M equals 1. If M equals 2, then between 0 and A I will have two half waves, and so on. So the M and N is the number of half waves in the different directions, in the X direction and the Y direction. So if I have a plate, can you see, or is it too shiny because of the sun? No, you can't see. We'll do it here. If I have a plate and I look at it by making a cut here, let's say it's under this kind of loading. If it looks like this, this is the shape at this location here. I have one half wave, M equals 1, let's say in the X direction. Now if I were to make a cut and look at it this way, if I saw something that involves two half waves, then I would have N equals 2. And essentially, my shape, if I could draw it, would look like this. Looking from the top now, I have one half wave in this direction and two half waves. How do I draw this? I don't know how to draw it. I have two half waves. Yeah, I know. It would look like this. So I have two half waves in this direction, and at any location, if I look at it, wherever I am, I would find one half wave. Now, if these are two, one is coming towards us and one is going away. So the message, M is the number of half waves in the X direction, N is the number of half waves in the Y direction. I hate this. Next time I should do something about that. Let's take the case. This is ridiculous. I can't see. Biaxial compression and Y equals, okay. Uniaxial compression, that's what that says. Yeah, supposedly. Makes noise but doesn't do anything. Miracle. All right. So this is the case that involves both the uniaxial compression, the compression in one direction and tension or compression in the other, expressed by positive or negative values of K. If I only have single compression, then Ny is 0, which means the K that's shown there would be 0. And therefore, this is my buckling load for uniaxial compression. And if I look at this one now, this buckling load is a function of M and N. Same way this buckling load is a function of M and N. Now, for the case of the biaxial loading, you have to find which combination of M and N values minimize this, and that is the lowest buckling load, or the buckling load in which a perfect flat plate would buckle into. In a sense, if you imagine you start from 0 load and you are increasing, then it will buckle when the lowest load starting from 0 is reached. So any expression that you have describing a buckling load, if it's a function of any other parameter, you have to minimize with respect to that other parameter. So in general, you would have to find here the M and N that minimize this, and for non-zero values of K, it's not at all obvious which value minimizes that, because it's a function of the D matrix and a function of the aspect ratio. In the case of uniaxial compression, it's slightly easier. Once K disappears, if you look at this, N appears only at the numerator, which means if I'm trying to minimize this, the smallest value of N, because all the terms involved are positive at the numerator, the smallest value of N, which is N equals 1, will give me the buckling load. So if I have uniaxial compression of a plate, then the number of half waves perpendicular to the load, so in this direction, is 1. It will only have one half wave. So you can impress your friends by telling them that you can derive that or prove it, that it will always be 1, no matter what the stacking sequence is, as long as it's symmetric, and D16 and D26 is 0. Still, after I set N equals 1 in this expression, I still have M, and if you see the M squared at the denominator, M fourth here, means I'm left with an M squared here. The M squared cancels the second term, M squared in the middle, and it becomes an M squared at the denominator. So actually, there will be some cases where M equals 1 or 2 would give you the lowest, but some cases where M equals 15 or 20 will give you the lowest buckling load. If I plot, because the other parameter besides M is the aspect ratio, so length divided by width is my aspect ratio. I pick a laminate which has the D matrix shown here, and I plot my critical buckling load in newtons per millimeter as a function of aspect ratio, and you will find that that critical buckling load changes with the number of half waves. That is, given this D matrix, if my aspect ratio is less than this value here of around 1.2, 1.4, then I buckle with M equals 1, which means I have only one half wave in that direction. Otherwise, if my aspect ratio is between this 1.4 and 2.6 or so, it buckles at M equals 2 with 2 half waves, and so on. If you increase further the aspect ratio, that is, the length becomes significantly bigger than the width, then you get M equals 3, and you can keep on doing that, of course, ad infinitum. You can get M equals 4 and so on. Interesting is that at the intersections of these curves, the analysis says you have two buckling modes coexisting. That is, the structure should buckle at the same time with one half wave and 2 half waves at this point here at around 1.4. Obviously, in reality, it never happens. There are eccentricities and imperfections which will favor one of the two. And depending on those, you will go either on one of the two, either on M equals 1 or M equals 2. How would that compare now to an equal thickness aluminum? Aluminum is much better. Basically, it can be anywhere between 10 to 20% better. Basically, the exact same equations we derive for composites can be used for aluminum. You just set your E values equal in all directions, and you rederive your ABD matrix, which is much simplified. Then you can actually use the same equation and get the curves for aluminum, which have the exact same shape, one half wave up to 1.4 or so, and 2 half waves up to 2.4. Keep in mind, for aluminum, these are exactly the curve. For composite, you will get this curve for this layup. If you change the layup, it will change the curve. But for purposes of comparison, basically, aluminum appears to be much lighter, or not much lighter, have significantly higher buckling load. But you have to account for the densities, obviously. So if I have the same thickness, aluminum is 10 to 20%, depending on the aspect ratio, better in terms of buckling load. If I now said I want to make my composite to match this, and let's say I want to match the worst case, the 20%. So I say I need to increase the thickness of my composite by a factor 1.2 to the 1/3. And that is 1.063, or I need to increase it by 6.3%. So we'll stop here, but first you'll have to tell me why. How I came up with this. I say I want the composite, which was 20% lower, had 20% lower buckling load, to have a thickness that is given by this quantity, 1.2 to the 1/3. So you expert engineers, how did I get it? That's right, only in thickness. But why is it this value? How did I come up with that? Okay, that's the 20%, very good. Where's the 1/3 coming from now? You are almost halfway there. Only thickness, and so? It is only thickness, yes. Yeah, but it's not the volume. Homsha? Yes, from now on you are excluded on answering any of the questions for the next week or so. But yeah, he's absolutely right. The D matrix, whether it's for isotropic material, we said it's EH cubed over 12 times 1 minus nu squared, or the Dij for a composite material, go like the Qij times Z cubed K plus 1 minus Zk, or whatever we cubed. Now this cubed means that if I want to, and because my buckling load is proportional to the D matrix, remember at the bottom here it's proportional to the D, so I need to increase my D by that 1.2 factor, but because it goes like thickness, where am I? It goes like thickness cubed, then I bring it over to the other side and it becomes 1/3. So that's the 1/3, and therefore that's my 6.3%. If I now try to compare the weights, that means that I have the density ratio, 0.58, that's about the density of carbon and epoxy to compare to aluminum, times my increase in thickness, 1.063, the width and length of the plate stays exactly the same to compare 1 to 1. And I see that the graphite epoxy or the carbon epoxy is 61% of the aluminum, or 38% lighter. So that is very encouraging. You say, okay, composites are 38% lighter, but this is only part of the story. We did this very roughly, and in reality the material, composite material, comes in distinct ply thickness. You cannot get any ply thickness you want, which means when you find this 6.3% increase in thickness, most likely you have to round up to the next ply because it will not correspond exactly to a certain number